Very much. It's a little bit more organized than last time because I miscounted my time last time. But which is the pointer now? Is there a pointer on this? Oh, it's just that one. Sorry. Okay. Okay. So this is kind of the title, the second of my lecture. So last time you have seen this Hamiltonian, although this constant, it was denoted by kappa. And anyway, this x is just a constant particles on the line, trigonometric Sutherland Hamiltonian, just a kind of introduction. And then there's the spin version, when this is a anti-Hermitian matrix with zero diagonal, the spin variable, and Lie algebraic generalization when you have some this psi alpha was referred to root system. And okay, so this we have seen last time. And actually, there's another model which is in this family, which belongs to my motivations, another kind of so-called spin Sutherland model. Same, and this exists only for the SLN type case, not for general Lie algebras. The same kind of interaction potential here, but this J is a kind of particle, and there's particles on the line, and every particle carries some d-dimensional complex vector. So it's kind of more physically motivated model. And maybe I mean, I probably won't have time to talk about generalization of this kind of model, but maybe it is certainly written, but we will not have time. So in this talk, I will talk about generalizations of the previous Lie algebraic kind of spin Sutherland models, which come by replacing the cotangent bundle in their derivation, which I will outline now by the Heisenberg double, the second kind of double. And this lecture is basically based on these papers here. Okay, so just very quickly, I remind you of this general setting which I'm working on. So I have compact, connected, simply connected Lie group with simple Lie algebra, then complexified Lie group, and then this exponential of I times the compact Lie algebra, sort of positive definite Hermitian elements, and the three doubles are cotangent bundle, the Heisenberg double, which I will talk about this today, the Heisenberg double, and the internal fused quasi-Hamiltonian double, which is the topic of the third lecture. And I mentioned without proof, but this is the important fact, that you have these rings of invariant functions on the group, on the Lie algebra, or on the space P with respect to conjugation action of the Lie group, and then you pull up these rings to the phase spaces. When G appears here, then you can view the invariant functions on the group as functions on the cotangent bundle, and so on. And all of these give Abelian Poisson algebras, which define some degenerate integrable system on those doubles. And I'm interested in the reduction of those degenerate integrable system by conjugation, kind of conjugation action. And in all three cases, these are some pairs of kind of matrices, let's put it this way, pairs of elements are pairs of matrices, and the compact Lie group acts by this kind of diagonal conjugation. And in some cases, this is a Hamiltonian action, or anyway, in all the cases has the property that the invariant functions form a closed Poisson algebra. So you can go to the quotient space and you obtain some reduced Poisson structure there. This is the main point. So I will put this transparency on the web page. So if you are interested, you can have a look. So I mentioned the definition of degenerate integrable system of symplectic and Poisson manifold. Basically, you have some commuting Hamiltonian, some Abelian Poisson algebra, and then some algebra of constants of motion. So the Poisson bracket is zero, and these algebras have the property of their functional dimensions add up to the dimension of the manifold. And in addition, the Hamiltonian vector fields of the Hamiltonian of interest are complete, which is automatic if the level surfaces are compact. And then this is a degenerate integrable system of rank R, and this is in symplectic manifold. And in Poisson manifold, the the addition is that we require also that the Hamiltonian vector field generated by H, they themselves are independent over pointwise over a dense open subset. Okay. And now I briefly, the example which I was discussing last time, and I plan to present this at the beginning of my talk, but I had no time, and so I skipped it. So let's go, this is a complement to lecture 1. So let's go back to the cotangent bundle, and this is the formula for the Poisson bracket. So never mind, so this 1 and 2 means derivative with the first variable, second variable. These are Lie algebra value derivatives. And you recognize the Lie Poisson bracket there. And this is the definition of the derivative with respect to group value variable. So behavior along one parameter subgroup. And then simply this Poisson algebra of commuting Hamiltonians are just invariant functions which depends on the Lie algebra element. And as I mentioned, the flows are very simple, just these orbits of one parameter subgroup. And then we go to the orbit space with respect to this conjugation action of the group. Okay? And how we describe the content of the reduced system, how this P-Sutherland model comes out is this. So first of all, so we restrict ourselves to some regular part of the phase space when this group element is regular. It has distinct eigenvalues, if you like, or the isotropic group is the maximal torus with respect to conjugation. And then we have to take quotient by the group action. By taking the quotient, you can bring the group element G to the maximal torus, and then it's called Q. So this is a kind of this regular part of the. I mean, the 0 means that the group element is maximal torus, and every orbit, it intersects every orbit in this regular part. Of course, it intersects it in many points. Namely, the intersection happens in orbits of the normalizer of the maximal torus. Okay, thank you. And so out of the invariant functions on this regular part, by restriction, you obtain invariant functions on this on this partial gauge fixing, which we call in physics, or maybe also in mathematics, a kind of slice for the orbits. And so this is an isomorphism. So every invariant function, the regular part, is represented by invariant function on this submanifold invariant with respect to normalizer of the maximal torus. So you transform the Poisson bracket from here to this space, and then I call this reduced Poisson bracket, which you obtain in this way. And this is the form of the reduced Poisson bracket. Again, derivative with respect to the first variable. Now the first variable is maximal torus value, so although it is, so this derivative varies in the dual space of the Lie algebra of the maximal torus. And here you have some interesting object which is called the classical R-matrix, a classical dynamical R-matrix. So this is similar to if you know the R-matrix structure, but this R here depends on the element in the regular part of the maximal torus, and namely it is given, if you write it like exponential form, it is given by this formula. So this is a linear operator which acts on the compact Lie algebra, and it acts by 0 on the maximal Abelian subalgebra, and it acts by this formula on the orthogonal complement of the maximal Abelian subalgebra, orthogonal complement with the killing form. So anyhow, this is the formula of the reduced Poisson bracket. And then the reduced equation of motion, or the Hamiltonian vector field, if you like, this dot, it looks like this. You will see here a kind of Lux equation. This dot means with respect to the decomposition of Lie algebra in the maximal Abelian part at the orthogonal complement. So the point is that you have this reduced Poisson bracket. And then variables were Q, maximal torus element, the Lie algebra, and J. And now the Lie algebra element, you take a certain parameterization. So this is the maximal Abelian subalgebra part, and the psi of these E alphas are root vectors with respect to the root system. So you can easily convince yourself that every element of this Lie algebra can be uniquely parameterized in this manner. And if you insert this parameterization into the you insert it into two places. You insert it into the main Hamiltonian, the kinetic energy. then you discover that this is the spin-Sutherland Hamiltonian. And you also, of course, ask how the Poisson bracket looks like in terms of these variables. And then it turns out that the Q and P are Darboux variables with respect to each other. And the psi variable, which is here element of the compact Lie algebra, which is orthogonal part to the maximal abelian. So this is which is called the spin variable. This actually matters up to conjugation, up to action by the maximal torus, because which is part of the normalizer, and it actually belongs to this reduced space of Hamilton reduction of the dual of the Lie algebra with respect to the maximal torus, which is denoted by G0 here as a zero moment mapped value. So I don't. So this is how the spin-Sutherland model comes out here. Okay. So very good. So the rest of the talk is. So I talk about this Heisenberg double and some similar integrable system only as in the cotangent bundle case. And then reduced integrability, which is quite similar to what I presented at the blackboard, but in a different context. And then description of reduced Poisson bracket and connection. So I'm going to obtain some integrable Hamiltonian systems. They turn out to be some kind of deformations of this spin-Sutherland model, and I want to discuss this deformation. And I'm pretty sure that I will not have time for what, if time permits, that's a very optimistic scenario. But I have written even some appendix, for which there will be no time, for sure. Okay, so some preparations, which partially it was already done. So compact Lie algebra, maximal abelian subspace, complexification, decomposition with respect to positive roots, negative root parts, and then you can decompose this complex Lie algebra regarded as real as compact plus another subalgebra, which is like this: the I times the maximal abelian subalgebra compact plus this thing associated with positive roots. So in the SLNC case, this is just the upper triangular matrices with real diagonal entries. This decompose, it will play a role. So every element you can decompose the G part, B part, or you can take the triangular decomposition, or you can decompose it into something in the compact and something I times the compact. All notations, and then there is complex conjugation with respect to this compact Lie algebra, which is actually the Cartan involution of this real simple Lie algebra, which is the complexification regarding the real. And okay, so there is then we need the group corresponding to this Lie algebra, and on that group there is also Cartan involution, which anyway this Cartan involution is nothing but the adjoint inverse, sort of in concrete matrix realization of these classical groups. You can always arrange this. That's why I denoted by dagger that this is actually really the matrix adjoint in concrete realizations, like in Knapp's famous book. It is done in this way. Okay, I need this. And then an important role is played by Iwasawa decomposition of the group element of this complex Lie group. So the Iwasawa decomposition is in the SLNC case, it is a Gram-Schmidt procedure that you decompose the SLNC element as unitary and something upper triangular with positive diagonal elements. So in general, suppose we have some element K of this complex Lie group. We decompose it in two ways. This G always means element of the compact, and the other guy, the B, means element of this kind of Borel group corresponding to this Lie algebra. The inverse is just inserted for some reasons of convenience. In other words, this B part is what people call in Helgason books and so on, A times N, some abelian and nilpotent part. So then there are these Iwasawa maps, so every group element. I mean, you have this map, this psi and lambda maps from, which is written here. This will play a role. And this irreversible decomposition is a kind of, it's unique, and it gives a diffeomorphism from the complex Lie group into these targets. And so our phase space will be now this complex Lie group regarded as real Lie group, but we use three models of it. One model is just itself. The other is by the irreversible decomposition, G times B. And the other is that the B group is itself diffeomorphic to this space which I called P. This is the P, and this diffeomorphism is this shortly kind of BB dagger map. So in this way, you obtain an isomorphism between the Borel group and the space of positive definite. So you factorize every positive Hermitian matrix as an upper triangular and its adjoint, unique factorization. And so in this way, we have three models of this manifold, which all of them are useful for various purposes. Okay. Sometimes this so-called dressing action of the group G on the group B comes up, and this dressing action is obtained in such a way that you multiply the element from the group B by the compact group element eta, and then you take its irreversible components, this B component from the left, and this gives you an action of the group compact Lie group on this Borel group. Okay, so this was so now on the phase space, on the complex Lie group regarding the real Lie group, we have two Poisson structures which I written here. So what is this notation here? I probably wrote it in the previous transparency, I don't remember, but anyway, this I means the imaginary part of the Killing form. This is the real invariant bilinear form on this complex Lie algebra, regarded as a real Lie algebra, which we use. So imaginary part of the Killing, in the imaginary part of the complex Killing form. And this rho, I mean, there are these derivatives. These derivatives are the usual left and right derivative on the group. So measure the behavior along one parameter subgroup from the left or from the right. So these are basically just extra derivative transported to the unit element by left and right multiplication in other words. So this Nablas are Lie algebra value derivative on this complex Lie group, and the rho is we have projection from the complex Lie algebra to the compact and to the Borel, and difference of projections to these things. This appears in this formula of the two Poisson bracket plus minus. And the plus Poisson bracket, these are Bernoulli Poisson bracket in Poisson Lie group theory. The plus Poisson bracket is actually symplectic, and this is called the Heisenberg double Poisson bracket. And the minus Poisson bracket actually gives this group a structure of a Poisson Lie group, which is that the group multiplication is a Poisson map. But this will not be important for us. Of course, it's important somewhere, but it's not necessarily needed now. So what is needed, if you take the, or just mentioned, is also not very important. If you take the minus Poisson bracket, which is a so-called Drinfeld double Poisson bracket on this complex Lie group, then both the compact group and this Borel group are Poisson subgroups. So it means that they are Lie subgroups and also Poisson submanifolds. So every Hamiltonian vector field is tangent to this subgroup. So they inherit some Poisson structure from the minus bracket. And these are written here, these inherited Poisson structures. Here the derivatives are again, Lie algebra value derivative. Not very important. So this right derivative, left derivative. On the compact group, of course, the dual space of the compact is identified with this Borel Lie algebra with respect to this invariant form. And so these derivatives for the compact Lie group, this is B valued, and derivative on the Borel group, this is G compact valued. And these are actually Poisson Lie structures on these groups. Actually, this symplectic structure, this plus Poisson bracket, which was introduced by Semyonov-Tianshansky, one of the founders of Poisson Lie group theory, in addition to Drinfeld. So this plus Poisson bracket comes from this symplectic form, which was actually found by Alexeyev and Malkin some time ago. So Okay, and then these maps, if it comes from irreversible factorizations, these are actually Poisson maps. Okay, but it's not very important for us. So what is the master system on this Heisenberg double? So I'm now using the model, which is this G times P. This is the model of the phase space which I'm using. So I take the irreversible decomposition, and then I map the Borel group to this by this Borel element B mapped to BB dagger, which is this positive element. And I use this as a model of my phase space. So before giving so this is the formula of Poisson, the plus Poisson structure in terms of this model. So the element is G, compact group element L is this from space P. And well, again, derivative is the second variable, first variable. This is my notation. Of course, derivatives are taken at this point. So, well, the derivative is defined here. There is some function on the P space. Then I will have this derivative is values in the complex Lie algebra. So the derivative has a compact component, which is defined by this formula. The x is taken from the Borel Lie algebra, and you look at the behavior of the function along this curve, and then y is taken from the compact Lie algebra. So the first part fixes the components of the derivative in G, and the second part fixes the components of the derivative in the Borel. And then the group, for the group valued variable, the derivative is in the Borel subalgebra, which was already mentioned. So never mind, you're not supposed to remember this formula. You see that it's very simple, relatively simple formula for the Poisson structure on the Heisenberg double, which is written there. It just comes from the original formula in terms of these variables. Okay. And then
you transfer.
Can you say it a little bit more?
Yes, my question is about this bracket on M. Where does it come from? You say that it's transferred from G, the Poisson bracket on G cross P. Where does it come from?
Yes, P times P. Yes, it comes from yeah, I understand. So it comes from the group B. I mentioned that the group B is a Poisson submanifold of this with respect to minus bracket on the complex group. So this is the inherited Poisson bracket on the group B, and B itself is diffeomorphic to P by this BB dagger map, and this is how the bracket comes. Is that it? Yes. And then now I'm going to, so now I'm come to the integrable system. So I first defined what are the interesting Hamiltonians. So the interesting Hamiltonians are just invariant functions on P pooled, regarded as functions on this M, depending on the second component. And then the constants of motion is actually arbitrary functions on this P times P. And I have a map, which I call the map of constants of motion. I wrote this in the Blackboard similar map yesterday, from my manifold M to P times P. And this map is just given by this formula. Here is the same formula as yesterday, just with different variables. And the point is that every function which is in this pullback is Poisson commute with every function which is from H. H itself is an abelian Poisson algebra. And so this every element of this, every function which is from here is a constant of motion for every time development governed by Hamiltonians from there. Okay, and then I actually give a proof that that you can count the functional dimensions of these things, and so here is the flow or the solution of Hamilton's equation, which belongs to the function from this H. The function is given by some function phi, which depends on L, and this is derivative of the function, which is in this case is compact valued because it's an invariant function. So derivative is compact valued, and again this is the integral curve, and so that's why this L is constants of motion, and also this other guy is a constant of motion. And then you count the functional dimension of this one is the rank of the Lie algebra, and the functional dimension of this one. This one is the, I mean, yes, it's the dimension of the phase space minus the rank. So I don't give the proof because then I will lose time, but the proof is there. Okay. So then the reduction procedure is just that I take this conjugation action, and this is an interesting action, how it comes from, but I don't explain this. It is orbit equivalent to a Poisson action generated by moment map, but it's not a Poisson action. And so because for that reason, the invariant functions form a closed Poisson subalgebra. So then this red always means reduced phase space. So you can view functions on the reduced phase space as these invariant functions, and basically, and then you let us pull back only the invariant functions from this p times p. P minus means that the first copy is active with minus that Poisson bracket which Cornelia asked about. So there's a Poisson bracket on p, and the minus 1 times is also a Poisson bracket. The two copies Poisson commute, and then this psi is actually a Poisson map with respect to that bracket. So the invariant elements of this f come from invariant functions on p times p. Okay, so they give functions on the reduced phase space. Well, this is very good, but since this is not a smooth manifold, then I don't want to now work with stratified spaces and all that. The theory also exists, but it's rather involved. And this is almost something like this, almost differentiable or whatever. It's complicated things. So I just want to work with honest, smooth C-infinity manifold. So for that reason, I go to the principal orbit type in my manifold M. And the principal orbits are just so that the isotropic is just the center of the group, center of the group. And this is a dense open subset, and no Hamiltonian flow can leave this dense open subset. So it's perfectly like, of course, I leave out something from the phase space, but it's very little what is left out, and it's sort of legitimate, at least in first approximation, to look at this dense open subset F star, principal orbit type, and okay, so the isotropic group is the center. And then there's an important, I'm coming to this diagram, which was also featured yesterday. So the C is the image of my constants of motion map. It's also not a smooth manifold, but I restrict to its regular part when this L is regular. So it's isotropic with the conjugation is maximal too. So in other words, so morally speaking, has different eigenvalues. And this is an embedded submanifold there. And then I go to the principal orbits inside this C reg, which is denoted C star. The isotropic, there is again the center. One can show this by this maximal Turain opposition in constant. Anyway, one can show this. And then I obtain this diagram. So this M double star is the inverse image of C star by the map psi. And I denoted this restricted map by just little psi. And in this diagram, these are the projections by the group action. So, but as only, so the isotropic group is the same. It's only one orbit type. So these are the quotient spaces by the group action. These are smooth manifold, and everything here is a smooth submersion and this Poisson, smooth surjective submersions and Poisson map. So for that reason, whatever function is here, I pull it here, it will be pull it back to my reduced phase space, this part of the reduced phase space which comes from this M double star. Then it will give constants of motion, and I can count the functional dimension of these constants of motion, dimension of this manifold. I can count these dimensions, and then in this way I obtain this theorem. So that this is I call it restricted reduced system. So restricted to this dense open subset of the principal orbit type, and the Poisson bracket there, and then there are the original Hamiltonians, which were invariant functions restricted there, and then I call this F sharp, yeah, like yesterday, the functions which come from this reduced space of constants of motion, and then the claim is that this is a degenerate integrable system in the sense of the definition which I said. In addition, more is true that the Hamiltonian vector fields are sort of the Hamiltonian vector fields coming from this H double star spend an r-dimensional subspace not only generically but every point of this part, and also this extra derivative of functions from this f sharp, they span the correct dimensional subspace of the cosine at every point, not in the definition I only require generically, but not generic everywhere it is true. So in a way, this is part of the reduced phase span. If you know this theory that the Liouville tori really exists, there's no singularities here, nothing. So in a way, this is not the interesting part to be because interesting things happen at the singularities. But so this is one of the main theorems. It is quite the same theorem as I said yesterday for the cotangent bundle. So now maybe you can understand it better. And then then I can extend the integrality statement. So there are two further results. The one result is that let's look at symplectic leaves, and the symplectic, at least the symplectic leaves of maximal dimension, there is secretly a moment map in this business, or momentum map. I call it moment map. So the moment map is this: the product of the left and right irreversible decompositions, and then this you can map also into P by taking B dagger, and then you take an invariant function there. And this will be a Casimir function this is a Casimir function for the reduced Poisson bracket. And there are R independent Casimir functions, invariant functions. So the generic Poisson submanifold are obtained by fixing the values of those Casimirs. And for that reason, the generic Poisson submanifold have codimension R in this reduced phase, where R is the rank of the Lie algebra. So in this way, you prove that the Hamiltonian vector field, since the Hamiltonian vector field never vanished here, so they are of course tangent to the symplectic leaves. So you prove that the degenerate integrability also holds in this every symplectic leaf of maximal dimension in this M double star. Okay, so this is this is any symplectic leaf of codimension R, degenerate integrable system. Fine. The R equal 1 case is just excluded because this is SU2 and the dimension is too small, so you don't have enough functions. So this is just only Liouville integrable, not degenerate integrable. Yes?
There you mentioned this Poisson-Lie moment map.
Yes.
It is a group-valued moment.
It's a group-valued moment map.
For the action, for which action is it?
I will explain it, but it takes some time. Okay, so maybe at the end of the lecture I explain this.
No, just.
Yes,
but I was just asking about the action of B on M.
So this moment map generates the action of G. B is a dual Poisson. It is analog of the dual of the Lie algebra. This is the dual Poisson-Lie group.
Okay.
But I can explain it, but I think it would take some time. And the point is that the action, this conjugation which I said, has the same orbit as the action generated by the moment map, and that's why I can use it for the reduction. And it is just simpler to present.
What is the psi? Like, what is that geometrically? You just defined it, but is there like a geometric the psi, which you defined as a
psi?
Yes, which you then used to pull back, like on your previous slide.
Mm-hmm. So this psi.
Yes. So what is that geometrically? Is there like you just defined it, but is it?
It's very natural. If you have the formula, is you can see it's extremely natural. Yes, this is the formula. And it is here. You see, it is just, if you like, geodesics or compact Lie group, then the two momentums, left and right moment maps, left and right multiplication, the momentum for the left and right multiplication, the kinetic energy coming from the killing form, they are constants of motion. And this is just that. In the Poisson-Lie context. Yes, it is that. There are two moment maps. Okay. Okay. So then I can extend this integrability statement to this full smooth part of the reduced phase space, this M star, which is M double star, so dense open subset inside M star. And how I extend this? There is some argument that the pullbacks of coming from this F and this F sharp, they have the same functional dimension. So this is some little invariant theory calculation which probably I don't have time to go into. So the point is that this is the theorem that this is also a degenerate integrable system. I mean, for the principal orbit type part. Proof proof is given in my paper. Now, okay, so I think I'm behind by 5 minutes according to my friend, but that's probably okay. So now I will come to some concrete description of these systems. What are these systems? Like previously I had the Spin-Sutherland model. So what kind of systems do I have? I have shown abstractly their integrability, but what are they? So first I present a description of I have two descriptions of the reduced Poisson bracket. Like in the cotangent bundle case, I have two descriptions, some abstract one and some concrete variables. So the abstract one, again, I go to the regular part of the phase space in the sense that the group element is regular. So then there is this gauge slice in my regular part, when the group element is transformed into the regular part of the maximal torus. And then this quotient space is actually the same as the quotient space of this gauge slice by the normalizer of the maximal torus. So an invariant function there is the same as an invariant function on the smaller space, but the invariance with respect to the normalizer of the maximal torus. So I can transform the Poisson bracket from here to there, and in this way, what I obtain, I call it reduced Poisson. Of course, it's not a real reduced Poisson bracket because this space is in between the original manifold and the final quotient space. But the residual invariance is only by the normalizer, which is a relatively small group, just the maximal torus and the Y group. Okay. And so I define this, which I call reduced Poisson bracket, by restricting the Poisson bracket of the invariant functions to this gauge size M0. And then I have a formula for this. This is this theorem. And the formula, the same dynamical r-matrix appears as before. This is the same as before, but now regarded as a linear map on the root space part of the complex Lie algebra. And it is this. This is well-defined linear operator. And then the reduced Poisson bracket is given by this formula. Again, derivative is the first and second variable. The second variable is called L, which is p-valued. So the derivative is complex Lie algebra valued as the second variable. And this is, the first variable is torus valued. So the derivative is b0 valued there. Never mind. But here the r-matrix appears. It is also a relatively simple and nice formula. And you can use this, or you can directly compute how the reduced Hamiltonian vector field look like in terms of this intermediate stage between the reduced phase and the original space on M0. And this is how the reduced Hamiltonian vector field look like. Again, you discover here a Lux equation, and this is this derivative is g valued, and this is the maximal Abelian subalgebra part. I mean, with respect to this decomposition. This decomposition. Okay, and you can also write this Poisson bracket in terms of the other model of the Heisenberg W, which the other model was that we use B instead of P, and this is useful for some purpose. So this is the first formula of the reduced Poisson structure, and then the second formula. Now I introduce kind of nice variables, kind of Darboux variables, and some variables which I call spin variable, and this is introduced in such a manner. So I use now, instead of, I had this variable L was BB dagger, But B itself can be written as abelian part and nilpotent part, which is this. This is diagonal part, and this is strictly upper triangular part with ones along the diagonal in the SLN-C case. So there is this variable P and B plus, and there is the variable Q. So I have new variables. New variable will be lambda. So this Q and this B, I introduce Q P lambda. P is just here, and lambda is this group commutator. By the way, this is not guessed. This is sort of also derived by reduction method, by the shifting trick. It's naturally obtained. But the point is that this is, in this way, I obtain a torus equivariant diffeomorphism between these two kinds of variables, this space and this space. Here is P and here is lambda. And I described, I rewrite the reduced Poisson bracket in terms of this new variable Q, P, and little lambda. And the point is that in terms of the new variable, the reduced Poisson structure takes a very nice form. And this is the form of the reduced Poisson structure. So this means here that this, this Q, which is this capital Q is exponent I times little q. These are Darboux variables with respect to each other. The first two terms mean that. And this means that the lambda variable kind of decouples, has zero Poisson bracket with the Q and P variables. And this term itself, if you know something about this Poisson-Lie group business and symplectic reduction, then you can discover that this is nothing but this has the interpretation that you have the Poisson bracket on the group B, which I mentioned, and the torus acts on B by conjugation, and it has a moment map, and the moment map is just the diagonal part of this B, and so you set it to 0, and then you obtain. Where is it? Then you obtain this Poisson bracket on the B plus group. So this is the reduction of the Poisson-Lie group B by the torus at 0 value moment map. Similarly, as in the spin-Sutherland case, we have the reduction of the Lie Poisson bracket at the 0 value of the torus moment map. There's a perfect Poisson analog of that. Okay, and now I come.
Can I ask? So the previous slide. So the B0 is the A from the Iwasawa decomposition, and the B plus is nilpotent, and okay.
Yeah.
As a group.
Yes, that's right. So now I come to the comparison with the linear case, the cotangent bundle case, the spin-Sutherland case. So here I this is the same as in the previous page, that I have this reduced Poisson bracket in this coming from the Heisenberg double. And now I call now the linear case what came from the cotangent bundle. And in the linear case, the Poisson bracket is quite similar. We have Q and P, and now there the variable previously denoted by psi. So now I denote it by x, just to make life more complicated. But really the relation is that this variable, that there are here two models of the dual of the Lie algebra G. One model is just G itself. The dual is just G by the Killing form, and the other model is B by the imaginary part of the complex Killing form. And now here I am using the Now I am using the model. I take B as the model of the dual space of the Lie algebra G. Previously I took it to G itself, and then this is anyway. You can see the reduction of the Lie. This is Lie Poisson bracket there. Okay, this I already mentioned that what is written here in green. I already mentioned that this first formula that I just said it once more that this represents. The reduction, this G star is actually the same. This is identified with the group B, the dual Poisson-Lie group. And so in the nonlinear case, we have this. This is the third term, and in the linear case, this is the third term of the Poisson structure. Okay, so there's a very nice similarity. And here is again, I repeated the spin-Sutherland Hamiltonian. And now there's a proposition here, which is not called, in what sense, this is saying that the nonlinear Poisson bracket in some sense can be, the linear one can be taken as a kind of limit of the nonlinear one, some degeneration. In what sense? So I have this mu epsilon is any positive number, and this is the phase space in the linear case. This is Lie algebra B plus, and this is Lie group B plus. This is the phase space in the nonlinear case at this intermediate stage. And I take this map, which is just multiplication by epsilon, and here exponentiation, epsilon is there. And then by this is the torus equivariant diffeomorphism. And then by using this map, I transform the Poisson structure from the nonlinear case to the linear case, and there's also this multiplication by epsilon there. And I take the limit, epsilon goes to 0, and in this way, from the nonlinear Poisson bracket, this was this f at 0, I obtain this linear Poisson bracket. So this is related to the fact that the cotangent bundle is some degeneration of the Heisenberg double. This is a reflection of that at the level of reduced space. And now, I also what happens with the Hamiltonians. Now, the only thing now to note is that the lambda variable, this belongs to this n, B plus or n group. I use exponential parameterization, like exponential of sigma. And then, well, I can, never mind, this is not important. So the point is that I have to, here is the definition of this lambda. I have to express B plus in terms of Q and lambda. And this can be uniquely done due to some Lie theoretic machinery. And this is written there, but it's complicated. But the point, my variable is this sigma Q and P, and then I have some kind of interesting Hamiltonians. So to obtain interesting Hamiltonians, I take an irreducible representation of my complex finite dimensional representation of that group, and then this is basically just adjoint with respect to the unitary structure. And then I just take basically character to trace in the representation, normalize with some normalization constant. And so I apply this trace to L. This is L, this positive definite element, this BB dagger, but expressed in terms of the variable QP and sigma, where sigma is from this lambda. And then you find that it has this form. It has this form. And here you see something, this is the representation rho, so you see something that's very similar to the spin-Sutherland one, this exponential. This is some finite polynomial on this sigma, finite because nilpotent groups. Some kind of leading term here is spin-Sutherland Hamiltonian, if you expand also the exponential. And I call this a spin-Ruijsenaar-Schneider type Hamiltonian for, I will come to some Ruijsenaar for that. So this is, this is the one. So I can also, this again, the same thing is repeated here, just expanded the exponential. And this can also be formulated in such a way that this nonlinear Hamiltonian, this coming from the character with the same diffeomorphism mu epsilon, it recovers the spin-Sutherland Hamiltonian in this kind of linearization limit. Also, the Lux matrix, the L becomes, this is the Sutherland Lux matrix. So this means that these models, which I call spin-Ruijsenaar models, are some sense deformations of spin-Sutherland models. Now, in the SLNC case, I can make things totally explicit because in the SLNC case, instead of the exponential parameterization, I can just parameterize n by just matrix elements. And I can solve those equations, but it's, as my collaborator used to say, don't want to meet this formula in a dark night in the forest. It's a kind of, I learned this from one of my collaborators. So it's explicit and it's actually nice, but it's kind of complicated. And now, Now, yes, now an example, a concrete example. So because we have this term, so this means that if we take if we take a Casimir function of, I mean, this is, as I said, this is reduction of Poisson bracket on B, and there are natural Casimir functions there. The B is BB dagger is P, and P is positive matrix, which just trace of power and so on in the SLN case. There are R natural Casimir functions for this bracket. So the invariant functions coming from actually lambda dagger, or dressing invariant functions, if you like. So some symplectic leaves can be obtained here by fixing lambda to like fixing in a coadjoint orbit. Now this is this analog of coadjoint orbit here, and now there are. So now I'm looking at the smallest coadjoint orbit, of smallest dressing orbit, smallest dimensional phase, which of course is the best if we have less variables. So let's take this matrix. Y here is just some real number. So this diagonal, this exponential of diagonal, so this belongs to this space P. So obviously this is in the SLNC case. So this is the most degenerate matrix, which is not the unit matrix. So it just has two different eigenvalues. One of them with multiplicity 1, and the other one with the rest are the same. So let's fix lambda to the orbit of this one, to the orbit of this, orbit of that one. And then it turns out that this denotes this orbit, this OY orbit, the intersected with this because lambda belongs to this n to the upper triangular part. And it turns out that this intersection is the elements of this intersection are written here like this. This nu y is also very concrete, strictly upper triangular means one along the diagonal and upper triangular, very concrete matrix. So every element here is obtained by conjugation by the torus. But remember that we have residual invariance with respect to conjugation by the torus. So by this conjugation, we can totally fix lambda to be equal to this nu y. So it means that this term disappears from the reduced Poisson bracket because this lambda just becomes a constant. So in that case, the reduced Poisson bracket will be just this. There are just sort of, this is 2 times n, the dimension is 2 times n minus 1, because this is SLN case. The rank is n minus 1. And in this case, there was this equation, this equation, which here it was lambda, but now lambda is fixed to be this fixed matrix, and then you can explicitly solve for B plus, this equation for B plus. And here is the solution, this complex conjugate, here is the solution, and then you insert this exponential. You remember that Hamiltonian was exponential of P times B plus. This is B and trace of BB dagger. So in this way you obtain some Hamiltonian. Now it will depend on Q and P, and now there is a further change of variables from Q and P to this theta, which also is not a guess. There is a reason, which I mention in a second. But this is a canonical transformation between QP and Q and theta. And if you write this trace of BB dagger in terms of these variables, then this will be this BB dagger inverse. This will be this Hamiltonian. And in physics, or in the field of finite dimensional integrable systems, is a very famous Hamiltonian. This is the so-called trigonometric Ruijsenaar-Schneider Hamiltonian, which quantum mechanical level McDonald's polynomials are eigenfunctions. The hyperbolic version, when instead of this you have hyperbolic function, this has to do with the sine Gordon solitons. It's a finite dimensional dynamical system describing just the motion of n finite number of solitons in sine Gordon field theory. And the reason for this canonical transformation was that there is also, I mentioned that there is also residual Y group invariance, not only torus invariance. And actually, so the reduced phase space is actually the cotangent band of the maximal torus divided the regular part, and you have to divide by the permutation group, which is the Y group in this case. And it is this variable theta and q which transform naturally with respect to permutations. Not the original p does not transform. It's just not the usual permutation action. It is more complicated. So these are natural variables here. Okay, and strangely enough, I basically have 2 or 3 minutes. So really fantastic. I never finish my talk. Well, very rarely happens. Not never, very rarely. So because I'm on time basically. So I said dual system in a nutshell. So again, okay, so there are these models, and now this original model is the most convenient. So there are these Iwasawa decompositions, repetition, and now take invariant functions from the group and pull the invariant functions back to this phase space, which is the complex Lie group M. And this is another abelian Poisson algebra there. And again, you can calculate the flows of these Hamiltonians. The flow is kind of interesting. So you have some function on the group chi. It has a Lie algebra value derivative gradient. And you put here this I, initial value at the time 0. You put in the I. So this is actually in the space P. And then you have to Iwasawa decompose this. And then the solution of the Hamilton equation with this pullback Hamiltonian is given by this formula. So it's kind of so it is a nice kind of usual factorization form. In many integrable systems you have this. So more advanced people use Riemann-Hilbert problem and so on. But it's some kind of finite dimensional version of that. And okay, so this is the dual system, and the map of constants of motion instead of sine over side twiddle, and this is the map of constants of motion in terms of this Iwasawa decomposition. And now I pull back the functions by this map. I take invariant functions with respect to, I take invariant functions with respect to conjugation of the compact Lie group and pull them back by psi. Then I obtain another degenerate integrable system there. And in this case, I restrict that second degenerate integrable system to the same symplectic leaf as before, but I use different parameterization of the reduced phase space. Namely, I can either diagonalize G, the group element, or I can diagonalize L. Now I diagonalize L. And the eigenvalues of the diagonalized L basically will be this Q hats or the exponential of this Q hats. And this real part of trace of G, this now gives this Hamiltonian, which is very similar. This is dual Ruijsenaar-Schneider Hamiltonian. So the Ruijsenaar-Schneider one, here you had cosinus hyperbolic, and here you had cosinus. I should have written here. This would be there's a typo here. This would be sinus hyperbolic function here. So with respect to the previous one, the role of the trigonometric and hyperbolic functions is exchanged. So okay, so this is one result, and maybe finally, sorry. I just conclude that what I did here, so I constructed some Poisson-Lie deformations of trigonometric spin-Sutherland model, proved degenerate integrability after restriction to this principal orbit type subset of the reduced phase space, and on maximal symplectic leaves on that. Actually, recently I also proved integrability on arbitrary symplectic leaf there, but I plan to present this yesterday as the third part of my talk. This was the second proof, but I have no time for that. Probably I will write a paper about that pretty soon. I also studied the dual system, but not every detail. The dual system is when so there are two abelian Poisson algebras, and then two integrable systems, and two group theoretically naturally integrable systems. One of them is called, I mean, they are in some sense duality to each other, and they correspond to Poissonly duality between the two Poissonly group and this dual group. And in the Sutherland case, the quantization by quantum Hamiltonian reduction is well understood because originally you have cotangent bundle groups, so you know that how you quantize it, and the Peter-White theorem you use for functions L2 on the configurations, this is the group, and by some kind of easy part of harmonic analysis, you can perform quantum Hamiltonian reduction. But the quantization of this in this Poisson-Lie case has not been worked out. It's not. This is very, very interesting. And actually, tomorrow, there are two other, so I'm very interested in the Sutherland, so-called the Ruizenhuis models, Ruizen-Schneider models. And I mentioned two versions, but there are two other versions. One of them I will talk about tomorrow, so-called compactified version. But there is also the hyperbolic one, in which you have hyperbolic function both in the moment and hyperbolic dependence of the coordinates. And this is the one, the hyperbolic version, which has to be the sine Gordon-Soliton. So somehow physically the most important, the most interesting one. And for that, the symplectic Hamiltonian reduction theorem is not known. And this is my main problem for something like 10 years, but I have no idea how to solve this. And as I mentioned, in integrable systems, you usually have rational, trigonometric, and elliptic versions. So elliptic versions are also an open problem. Thank you very, very much.